Hi, this video will be about the gamma distribution. I'm going to define the gamma distribution via its density. So the definition is that X has the gamma distribution of parameters n and lambda, where n is, for the moment, it's a positive integer and lambda is a positive real. Okay, so X will have the gamma distribution of shape parameter n and rate lambda. Let me add this here. So this is the shape, this is the rate. If its density is of the following form: lambda to the n, x to the n minus 1, e to the minus lambda x over n minus 1 factorial. And there is a good reason it's called a gamma distribution. N minus 1 factorial is actually gamma of n, and a few minutes from now we're going to see that you can actually generalize this to non-integer n's. But for now, let's stick with the positive integers n, and so this is the density for positive x's, or non-negative x's, doesn't matter. Okay, now the first question, of course, is whether this is actually a density. And to see that, one thing you can do is, well, the thing you have to do is to check that this is non-negative. Okay, so is this a density? Probability density function. And the thing you check is that it's non-negative. Well, of course it's non-negative, nothing here is negative. The other thing you check, of course, is the integral from 0 to infinity of this function lambda to the n, x to the n minus 1, e to the minus lambda x over n minus 1 factorial. So everybody knows that we need to check that the integral from minus infinity to infinity of f of x is 1, but this is only valid for positive x's, and f is of course 0 for negative x's. Maybe I didn't say that, but okay, I mean that. F is 0 for negative x's. Okay, and so the integral will only go from 0 to infinity. Now, why is this 1? How can I see that this is 1? Well, if you remember my previous video on the gamma function, then this function here actually looks very similar to this integral there. There is a power of x, a power of y, an exponential of x, an exponential of y from 0 to infinity. So it's almost the same thing if we just change a little bit the integration variable. And the change of variables we need is very simple. It's just a factor lambda of x. So let's rewrite this integral into lambda times x, which is my new variable. So there is going to be a lambda times x to the n minus first power here. Let me just write this out for a second without substituting anything yet. I'm just going to regroup one of the lambdas into dx. Okay, so I have n minus 1 of them here. I had n there, but I have an extra there. So in total it's n of the lambdas. And now you can clearly see that where this is going. I'm going to substitute y here for lambda x. I'm going to substitute y there in the exponent as well for lambda x. And I'm going to substitute dy for lambda dx, because if y is lambda x, then of course dy is lambda dx. And now I can look at the definition of my gamma function. Gamma is actually defined exactly this way. So this is the gamma function at n, except for that n minus 1 factorial, which is a constant in the integral. So in fact, I arrive to gamma of n over this constant n minus 1 factorial. However, another thing we noticed with the gamma function is that gamma of n is indeed n minus 1 factorial for positive integer n's. So gamma of n is n minus 1 factorial, and that exactly gives me the required identity that the integral of this function here from 0 to infinity is actually 1. So this thing is indeed a density. Okay, now why do we like the gamma function? And here is why we like it, because at this form Here's a simple proposition. At this form, it actually comes from convolving exponentials. The proposition is that the n-fold convolution of exponential lambda is exactly gamma of n lambda. Okay, that's the proposition here. Okay, so let's prove this. To prove this, we're going to do induction. And so we're going to start with n equals to 1. Now the one-fold convolution of something is just the thing itself. Is it true that exponential lambda is gamma of n equals to 1 and lambda? Well, let's see. If I plug in lambda n equals to 1, if I plug in n equals to 1, then I have a lambda factor here. So the density, this thing has density equal to, according to our definition up here, so plug in n equals to 1, that gives me a lambda. So there is a lambda factor here. Plug in, this way you can see both. Plug in n equals to 1, so x to the 0, that's not giving any contribution. Plug in n equals to 1, well, there is not even an n there, so I just copy e to the minus lambda x. N equals to 1 gives me n minus 1 factorial, 0 factorial is defined to be 0. So the density is, for gamma 1 lambda, is lambda times e to the minus lambda x, which is the same as the density of the exponential function, so or exponential distribution. So indeed, n equals to 1 gives me that exponential lambda is the same as gamma. Okay, gamma of 1 and lambda. So now to do the induction, then we have to do the induction step. So I'm going to assume that is true for n. So assume that the thing is true, so n-fold convolution of exponential lambda is indeed gamma n lambda, and try to convolve gamma and lambda with yet another exponential and see if we can gamma of n plus 1. Okay, so try to do f of exponential lambda convolved with f of gamma n lambda, and let's see what happens. Take it, for example, at some point a. So the definition is that I go from minus infinity to infinity of one of these functions taken at x, the other taken at a minus x. Now clearly the exponential function is simpler, so that's the one I'm going to take at a minus x. So I take the exponential function at a minus x. There is no lambda yet. And I'm going to take the gamma distribution function at x, and I'm going to integrate them out. Now, the integral is only going to go from 0 to a. Why is that? So why do I only need to look at this from 0 to a? Well, both of these densities are 0 for negative arguments. So whenever x would go negative, then this density here would be 0. Whenever a minus x goes negative, so whenever x goes above a, then this will go 0. And so I only get contribution from 0 to a in x. And there I can just substitute the formulas I know for the exponential density and for the gamma density. So for exponential I have lambda times e to the minus lambda and whatever I see inside here. So that's a minus x, that's the exponential density. Okay, so this is this. And then for the gamma density I just copy what I had before. And what I had before was this. So I'm going to copy this down here. Lambda to the n, x to the n minus 1, e to the minus lambda x over n minus 1 factorial. So that's my gamma density. Okay, so this is f of gamma at x. And I need to calculate this integral here. But it's not very hard actually, because one thing you will notice straight away is that the exponential of x just goes immediately. There is a positive lambda x up there, there is a negative lambda x down here, They just go. So let's collect everything which doesn't have x in it. Lambda to the n plus 1 for the lambda factors. There is an n minus 1 factorial down here. There is an e to the minus lambda a. These are the terms which don't have any x in them, and then I have the integral from 0 to a of whatever is left is quite easy, x to the n minus 1, and that's it. That's it. I have all other terms factored out. Okay, and so this is an easy integration, lambda to the n plus 1 over n minus 1 factorial, e to the minus lambda a. And so now I'm integrating x to the n minus 1, that gives me x to the n over n taken at a subtracted at 0. And so when I take the thing at a, that will give me x to the, a to the n. When I collapse n minus 1 factorial with n, that gives me an n factorial. And when I take x to the n at 0, then I get 0. N is at least 1 in this argument. So I start the induction from n equals to 1 and I want to go higher, so n is at least 1. At least first power of 0 is 0. And there we go. We have the same density as before, except that n is increased by 1. Lambda to the n plus 1 instead of lambda to the n, a to the n instead of n minus 1 power, n factorial instead of n minus 1 factorial. So the convolution we started with actually turns out to be the density of gamma of n plus 1 and lambda at a. Okay? And that's what we wanted to see, because we wanted to add independent gamma and exponential random variables. We did the density convolution and we arrived to gamma. Of course, it follows from here that if I now do gamma convolution with another gamma random variable, gamma of n lambda convolved with gamma of m lambda, notice that the lambda parameter needs to be the same. If the lambda parameter is not the same, then I don't have this nice cancellation up here with the exponentials. So I need the lambda parameter, the rate parameter, to be the same. But in that case, I just have gamma of n plus m and lambda, where n equals to 1 would mean exponential, but this is of course true otherwise, because you just write this up as this many exponentials, this one as that many exponentials, together it's n plus m many exponentials, independent IID. Okay, so that's a very nice property of the gamma convolution. Now, here's another remark, that actually when we define the gamma density, we could have used here the gamma gamma function. So let's do that. So f of x, let's go back to this black color we had here. F of x could also be written as lambda to the n, x to the n minus 1, e to the minus lambda x over gamma of n minus 1 factorial for integer n's is gamma of n. But in this formulation, actually, we are not required to have integer n's anymore. So in fact, this works perfectly fine. In fact, everything works perfectly fine for defining the gamma of t and lambda distribution, where t and lambda are both positive reals. So the difference is that I can make the shape parameter, which used to be an integer before, I can actually make it into a real positive real parameter. It is not going to be the convolution of exponentials anymore by itself, but it will still have all the nice properties. So let's start with the density. I could say lambda to the t, and then x to the t minus 1, e to the minus lambda x over gamma of t is my new density for positive x's, and this makes perfect sense. It is going to be a density the exact same way as before, okay? one can still make the gamma convolution. It is still going to be true that convolving gamma of T lambda with gamma of S lambda is going to be gamma of T plus S and lambda. Notice still that the lambda parameters are all the same. Okay, we can still do this. It's still not very difficult integration to do. Okay, it's still true. One needs a little bit of beta functions to verify this, which I'm not going to do here, but it's still a completely fine integration, and one can easily do that for any positive T, lambda, and S parameters, reals. They don't need to be integer. Okay, so that in that sense, gamma is quite nice in general. Okay, let me then proceed to some properties of gamma, namely some more properties. Essentially, I just want to look here to the expectation. So what is the expectation? So let x be gamma of parameters n and lambda, and let's do the expectation of x. And one way, of course, could be to integrate this out, but at least for positive integers, I know that gamma is a convolution of exponentials, n-fold convolutions of the exponential lambdas, and that immediately gives me the expectation, and in fact the variance as well, as n times the expectation and variance of exponentials. So the variance of gamma will be n over lambda square, and the mean will be n over lambda, immediately from the convolution property. Anybody interested can also figure it out for non-integer shape parameters. In this case, actually that case, you can work out the expectations and find that this is still true for non-integer n's. Okay, and furthermore, since it's the sum in distribution is the sum of independent exponentials, you actually have a law of large number kind of things. What is the law of large numbers? If I look at the sum of NIID exponentials and I divide by n, it will converge to the mean of the exponentials. So instead of taking NIID exponentials summed up, I'm just going to take my gamma random variable here, and this will converge in some sense, which we can discuss later on in what sense, but it will converge to the mean of one of these exponentials, which is 1 over lambda. And in fact, the central limit theorem kind of statement also holds. If I look at x, my gamma distribution, and I think about it as the sum of IID exponentials, then I can subtract n times the mean of the exponentials, so 1 over lambda n times. I can divide by square root of n times the standard deviation of my exponentials, or square root of the variance, and this will converge in some sense, which we'll discuss later, to standard normal as it does in the central limit theorem. So that's some nice properties of the gamma distribution.